Hello. Today I would like to present my I would like to propose my design, my turbine design. So there are three things that I would like to present. First is my model turbine, which has been assigned in the group. So my group got placed at Central Kansas here, and this is my spec, spe mod, my mod, my modulation. Here I manage it to 30 meter and shear coefficient 0.2. For wind farm, I use for 9 turbine, and here are here there is a turbine layout map, which I use 3 turbine per row, 3 number of row, and I use a square shape, and turbine spacing and row spacing also 3. And for installation cost, there is estimate here that the total for the turbine cost for each one is 27,000 here. So um, after summing all with the balance system cost, the total will come to $75,428.10. And the total install cost per kilowatt is 7,619 per kilowatt. So there, the second model here, I choose the model Energy Ball HEA-V100 1.1 meter. The hub height is 4 meter and shear coefficient is 0.1. The wind farm here, for the wind farm, I use for the number of turbine in farm 55, and this is the turbine layout map, which I use the shaped triangle. There is 10 turbine per row and 10 row, and there is spacing, and row spacing is 9 rotor diameter. So when I simulate here, I forgot to show the installation cost. For installation cost here, the number on the cost, the total cost for each turbine cost here is for the 55 turbine here is $76,477.50. When we sum up all, we got the $209,522.50, and total cost per kilowatt is also same here, which is same with the other model, with the first model, which is $7,619 per kilowatt. When we simulate here, and also the first model, when we compare, the usage or the capacity here is different, which is the second model use a lot of capacitor than the first model. And also the net, here we can see the capacity factor here also decrease, which is not used, which is the usage is so little than when compared with the other one, which is we can see here the first model is the better model to use than the other one, the model 2. So we go to the third one. We go for the PV watt. Here, this is the place that I use, the same place. So here, um, for the system design here, I use 21.4 kilowatt DC, and DC to ratio for DC to AC is 0.5, and inverter efficiency is 96, because this is a desired number for desired percentage to use at that place at the central Kansas. So the tilt is 38 degrees, azimuth is 180 degrees, and ground cover ratio is 0.4. I use array type 1 axis tracking. For the array type, I use 1 axis tracking. So the default setting here I use. So the total system loss is 12.49% here. For the installation cost here, um, here after for the direct capital cost, the total direct cost here is 43,870. For indirect capital costs, the total is $90,688. So when we simulate here, as we compare with the first model that we choose, the difference is doesn't look so big. It's just a few, but as we can see, the net capital cost here is much less less is less, which we can see it the affordable here, which the pivot here is more affordable than the turbine, but we can see from the what we call the capacity factor here is really low, which is not efficient for the electricity produced to supply the 30,000 watt kilowatt here. So although the turbine has got a bit costly here, but still it's efficient. It's really efficient to use um, when we want to supply the electricity at that place. So I think from here we can conclude that the model turbine here, Chrysler 300i 3 meter, each desired to use as a their turbine here to use as a electricity supplier here. Then we use PV watt here. So that's all from me, and thank you.